Assalamu alaikum. So in continuation with the network optimization, so in the last lecture you saw that we come to the point where we get the optimal diameter and which takes this form. So remember that we want to optimize the diameter, right? And so what we need to know here the friction factor, but without knowing the diameter you cannot know the friction factor because the friction factor comes from the Reynolds number and epsilon over d. So you should know the Reynolds number and you should know the epsilon over d. That is for turbulent flow. And even if it is a laminar flow, you should know the Reynolds number. But Reynolds number comes from rho v d over mu. So it depends upon the diameter. So basically you cannot calculate the friction factor without knowing the Reynolds number, without knowing the epsilon over d. So this is basically a cyclic process. You want to find out the diameter. Diameter depends upon the friction factor, and friction factor depends upon the diameter. So it can be solved iteratively. So there are two procedures to solve it. One is the iterative and one is the direct method. So we will see these two schemes to find out the friction factor. So here is that the scheme to find out the friction factor. So this is our d optimal, and we just like reverse this expression, and when you reverse this expression then it takes this form. This is our d optimal, right? Then we are multiplying both sides by 4m by pi mu, and which gives us this expression. All right, so with this expression, when you take this power, on the right hand side, then it takes this form. It takes this form, and on the right hand side you have this thing. Now this here, what does this become? This becomes the Reynolds number. That was the purpose, to multiply by this quantity. So now it becomes a Reynolds number, and this f can be taken on the left hand side by multiplying both sides by f. So here you multiplied by f, and then this f would be cancelled here, so there is no f here. And so here you multiplied both sides by f, so this is the equation that you will get. Okay, so now what we can do with this equation, so we got this equation, so what we can do with this equation? Okay, so with this equation we will try to set up a method to find out the friction factor. So friction factor is non-dimensional and independent, and Re also non-dimensional and independent. Like independent we cannot say because the Re basically depends upon the other parameters, but it is a non-dimensional. Same thing happens with the friction factor, that this is a non-dimensional number. And here all the quantities like the mass flow rate and most of the quantities here are dimensional quantities. So what we can do, that these are the two non-dimensional numbers, and the multiplication again makes it non-dimensional. So when we have a non-dimensional parameter, then it can be used as a scaling parameter. It can be used as scaling parameters. And we also know that there is another term, epsilon over d, which is also related to the fluid flow, and this is also a non-dimensional number. So how can we use this number, and to set up a scheme to find out the friction factor? So we know another non-dimensional number, which is a roughness number, which is basically the ratio of your roughness ratio over Reynolds number. So which takes this form. So the roughness number is basically equal to this thing. Now, if you want to plot the friction factor, versus this quantity, friction factor versus this quantity. So remember that here all are non-dimensional scalar quantities. So this is friction factor, and this is friction factor multiplied by Reynolds number, right? So Reynolds number is non-dimensional, f is non-dimensional, and here f is same thing, and also it is non-dimensional. And The RO is again a non-dimensional. So we will see that how we can basically draw this thing, draw the plots between F and FRE and these with this expression basically. So now our objective is to draw the curve or set up a relationship between F and FRE this. So the relationship, we know that this is the relationship, but this relationship doesn't give us the diameter, right? So we want to set up the curve between these two. Our objective is to find out the F. So if we know this quantity, then we can calculate the, then we should be able to find out the friction factor if we have the curve like. If we have some sort of curve like that, here we have F and here we have F R E to the power n plus 5 and this whole to the power 1 by 6, and if we have some sort of curve for this, then we can find the F. So we need to draw the curve. So how can we draw the curve, right? So that we will see here. So let's say that you choose any value of RE, any value of RE which is random in turbulent regime. So if then you choose any value of epsilon over d. So of course that you are choosing these some reasonable values that actually exist. So you're choosing the epsilon over d. And then you calculate that what is your value of RO. So your RO value is epsilon over d RE. So now you have the epsilon over d and you have RE, so you can calculate RO, right? So your RO is known. Your RO is known. Now you have the epsilon over d and you have the RE, then you can go to the Moody's chart to find out the F. So you can find the F also. So you can find the RO and you can find the F from the Moody's chart because the epsilon over d is known and RE is known. So substituting these values, can we find this thing? FRE. So now see the expression, what does this need? So it needs F and it needs RE and it needs N, right? So you have to set the value of N, right? So you have to set the value of N. So let's say you set some value of N here. So the N, let's say you set the value 1.2. And then you have N, you have RE, you have F, so you can calculate this quantity, right? Similarly, you choose another combination, or you can keep the RE value same and you can just change epsilon over d, right? So you can calculate RO, you can calculate F, and you can this will remain constant 1.2, 1.2, 1.2, because this is, remember that this parameter comes from the pipe cost Cp, that's C1 d to the power n, and the C1 and n are constant, so n will remain constant here. Then when you have the RE, when you have F, then you can calculate this again. So similarly, you have to prepare this table and generate a lot of data for that, right? And then you have to see that the RO value, where is it? Same. So the data which represent the same value of RE, you can categorize them, right? And then later on you can plot them. So remember that we choose the n equals to 1.2. So our n equals to 1.2. And this expression is that what we calculated in the table here. This is right. So n1 plus 2, then this power will be 6 plus 2, and this will be 1 over 6 plus 2, 6.2, sorry, 6.2, and then 1 over 6.2. So we this is n plus 1, 6.2, yes. So we are here basically. I think I made a mistake here. This is n plus. Yes, there is some editing mistake here. This is actually 5 plus 1. This is actually 6. This is 6 constant, as we can see here. So this is 6 is constant, because this is what we are basically setting up the relationship. This is, so this 1 over 6 is constant here. Okay, so we can basically, so again, like we need to correct this, that this is 6 actually, 1 over 6. So so we select the RE, we select the epsilon over D, and then we calculated RO, we calculated F, and then we calculated this multiplication of F and RE, and the N value we choose. So we have an option that N equals can be 1, can be 1.2, can be 1.3, and that comes from the pipe cost relationship. So if it is 1.2, we choose, then accordingly uh, we can calculate this value. Okay, then with all these values, we are, because when we generate the lot of data here, and then we can plot the curves. So the curves we are drawing for N equals to 1.2, and this value that we calculated in the table, and this is the friction factor, and then when you join the points, then you get this kind of curves. So remember that the sum points showing the constant RO value. So we join the points where the RO value is constant for those points. So for these points, the RO value was constant. So this kind of curves we get. So these curves help us to find out the friction factor. For the given problem, because these are all independent, all non-dimensional numbers basically. F is non-dimensional, RE is non-dimensional, and RO is also non-dimensional. So how can we use with these curves to solve our problems? Then we will see it through the problem. So as I said in the beginning, that when you have this d-optimal expression, and we cannot find the d-optimal because we do not know the F, so it becomes a cyclic process, because the F need RE and RE need diameter, so it is a cyclic process. So for the F you need RE, and for the RE you need the diameter, and again it becomes cyclic process. Like if you want to find out the optimal diameter, then you need to know F. So the second method for this is the iterative method, that in the beginning you will use certain value of either friction factor or optimal diameter, and then you try to reduce the uh, residual to find out the optimal value. So we will see through an example both of the methods when we do the example. Okay. Thank you very much. Assalamu alaikum.